Hi, this is lesson or chapter 10, part 1, Networks and Telecommunications. The topics: what is the Open Systems Interconnection OSI reference model? What the main types of network are? What TCP/IP is and how it works? What network security risks are? What basic network security defense tools are? How wireless networks work and what threats they pose to network security. The Chapter 10 goals were to describe the OSI reference model, understand network types, network protocols, and network security risks, understand some basic tools to defend against network security risks, understand wireless networking and the threats it can pose to network security. Our learning objective is to describe networking principles and security mechanisms for networks. And the key concepts are the OSI reference model and its security lapses, physical and logical network topologies, TCP/IP and how it works, network security risks and defense tools, and wireless networks and security controls. Let's talk about the Open Systems Interconnection OSI reference model, which by now you probably know contains 7 layers, starting from the top to the bottom, and the bottom is your physical layer, which is like your cables. The first layer, this is the top layer, layer 7, is the application layer. This layer is responsible for interacting with end users. The application layer includes all programs on a computer that interact with the network. For example, your email software is included since it must transmit and receive messages over the network. A simple game like Solitaire doesn't fit here because it does not require the network in order to operate. So we're talking about applications that need the network in order for them to work. Solitaire or any other game like that is loaded on the hard drive of your computer and you don't need to use the network to use it. Layer 6, the presentation layer. This is where data formatting and encryption occurs. This layer is responsible for the coding of data. The presentation layer includes file formats and character representations. From a security perspective, encryption generally takes place at the presentation layer. Layer 5 is the session layer. This layer is responsible for maintaining communication sessions between computers, or as it says, process-to-process communication. It creates, maintains, and disconnects communications that take place between processes over the network. The transport layer is layer 4. Its basic function is end-to-end communication maintenance. This layer is responsible for breaking data into packets and properly transmitting it over the network. Flow control and error checking take place at the transport layer. Layer 3 is the network layer. Its basic function is routing data, logical addressing, and wireless area network delivery, which, of course, the wireless area network is the internet. This layer is responsible for the logical implementation of the network. One very important feature of the network layer, covered later in this chapter, is logical addressing. In TCP/IP networking, logical addressing takes the familiar form of IP addresses. Layer 2, the data link layer, is where physical addressing and local area network delivery occurs. This layer is responsible for transmitting information on computers connected to the same local area network. The data link layer uses media access control, or MAC addresses. Device manufacturers assign each hardware device a unique MAC address. Every device has its own unique MAC address. The first few bytes of the MAC address designate or describe the manufacturer, and then the last bytes of the MAC address describe uh, the actual device and then its unique address that's associated with it. Layer 1 is the physical layer. Its basic function is signaling. This layer is responsible for the physical operation of the network. The physical layer must translate the binary ones and zeros of computer language into the language of the transport medium. In the case of copper network cables, it must translate computer data into electrical pulses. In the cases of fiber optics, it must translate the data into bursts of light. The one thing we must understand about the OSI reference model is that, first of all, when a message is sent from you to me, it has to go all the way down from layer 7 on your computer, all the way down to the physical layer, at which point it may actually use um, satellite communications as its physical layer at some point, and then send the message to me, and then go back up the OSI reference model through each one of these 7 layers and the functions that occurs there until it gets to me, and I can read your message. Now, another point about the OSI reference model is that using it allows us to break the process of sending a message from one computer to another into these 7 distinct layers. It allows us to work in the idea that if you have a problem, you can isolate it to one of these layers. Not only that, if you had to do maintenance to software that runs or hardware that runs on one of these layers, it would not have to be done. Upgrades or other kind of maintenance would not have to be done to any of the other layers. You have to change a router, you're working at layer 3. Go ahead and upgrade that router or fix routing table or do something else on it. That's handled at layer 3. You're not dealing with the software hardware working at layer 2, which typically is a switch working at layer 2. The main types of networks, wide area networks, of course, this is the most prevalent wide area network is the internet. Connects systems over a large geographic area, and local area networks provide network connectivity for computers located in the same geographic area. So wide area networks. The internet is an open network. It cannot guarantee privacy. Consider the security issues surrounding the use of an open network. Somebody could break into it. You could develop your own private wide area network, and there are primarily for 2 reasons. First, of course, security, and second, for the guaranteed reliability of private networks. Some wide area network connectivity options, cable modem, a lot of us use that in our homes. Digital subscriber line, DSL from the telephone company is hardly used anymore due to the speed and availability of broadband fiber optics, which of course is the next connectivity option. Satellite is used a lot to get data from one part of the country to another or one continent to another. Dial-up is still used, at least in the United States, probably not used in some of the more advanced European countries that are all on high-speed broadband internet, and a lot of America is not on high-speed broadband internet. Rural areas still suffer from the digital divide. Rural areas still suffer from that because they have to use dial-up across the telephone line to get their communications. The book talks about cellular 3 and 4G networks, but very few, if any, wireless is conducted over 3G networks today. This really ought to say 4G and 5G networks. We're approaching 5G connectivity for all, but even if T-Mobile or Sprint, well, now they're one company, AT&T or anybody else offers 5G networks, what your problem is that your device has to be a 5G compatible device in order for you to get 5G speeds. If you don't have a 5G compatible device, I don't care how fast you run the network, you're throttled down or limited by the speed of the device that you're connecting to it. Routers. Router is a device that connects 2 or more networks and selectively interchanges packets of data between them. A router connects a local area network to a wide area network by examining the network addresses to decide where to send each packet. First type that the book talks about is a border router. Sits behind a firewall, or should sit behind a firewall, protecting the internal network from the untrusted wireless wide area network, which is the internet. It's subject to direct attack from an outside source, and that's why it must sit behind a firewall. that the firewall must be between the router and the untrusted internet, which is the wide area network. You have interior routers. Interior routers can provide enhanced features to your internal networks, can be used to keep the subnet traffic separate, but that can also be done with a switch. Can keep traffic out of a subnet and traffic in a subnet. For example, an internal router that sits between the network of an organization's research and development department network and the network for the rest of the organization can keep the two networks separate. You can configure routers to allow all traffic to pass or to protect some internal resources. Routers that use network address translation and packet filtering to improve security. Network address translation uses an alternate public IP address to hide a system's real IP address. So when we talk about router placement here, we have a border router. It's subject to a direct attack from an outside source. When you configure any router, you should determine whether it is the only point of defense or if it is one part of a multi-layered defense. Of course, a multi-layered defense is far better and more secure. The lone defense router can protect internal resources, but is subject to attack itself. And as you see in this diagram, it should sit behind a firewall. Internal routers, which is in this diagram right to the left of the border router, can also provide enhanced features to your internal networks. Internal routers can keep subnet traffic separate, and as stated before, they can keep traffic out of a subnet and keep traffic in a subnet. For example, an internal router that sits between the network of the organization's research network, again, as mentioned before, separates it from the rest of the network. These routers can keep confidential traffic inside the department that's supposed to be confidential. And they can also keep traffic that isn't designated for that department out of that department. Here we have local area networks. Systems on the same local area network do not protect themselves from each other, so good security is important. Obviously, we have a switch here that connects one subnet within a local area network to another subnet within a local area network. Ethernet networks. The Ethernet standard defines the way that computers communicate on the network, governs both the physical and data link layers, defines how computers use MAC addresses to communicate with each other on the network. Ethernet has become the most common local area network technology in use. Local area network devices, hubs and switches. They connect computers on a local area network. Hubs contain a number of plugs or ports where you can connect Ethernet cables for different network systems. When the hub, not when they hub. When the hub receives packets, they automatically retransmit those packets to all the other ports. However, a hub does not inspect the packets and therefore does not direct the packets in any way, shape, or form other than the cabling that comes outside the port of the hub. Um, you cannot subnet a network using a hub. And the other problem is, as it says here, they automatically retransmit those packets to all the other ports. And so you're doing a broadcast that goes to everybody connected to that hub, as opposed to selective departments or selective subnets that a switch allows. Switches perform intelligent filtering. They know the MAC address of the system connected to each port, and when they receive a packet on the network, they look at the destination MAC address and send the packet only to the port where the destination system resides. So they are able to define broadcast domains where only data goes to the domain that it's supposed to go to. That subnet, data is broadcast to that subnet and nowhere else. Virtual local area networks, or VLANs. Any broadcast domain that is isolated from other domains. A collection of logically related network devices that are viewed as a partitioned network segment. Used to isolate logical groups of devices to reduce network traffic and increase security. Let's talk about TCP/IP, or the Transmission Control Protocol, Internet Protocol. We'll talk about how it works. A protocol is a set of rules that govern the format of messages that computers exchange. TCP/IP is a suite of protocols that operates at both the network and transport layers of the OSI reference model. It governs all activity across the internet and through most corporate and home networks. It was developed by the Department of Defense to provide a highly reliable and fault-tolerant network infrastructure. Security, though, was not a focus. And so TCP/IP, when it first became the de facto standard in 1983, security was never considered. And that's why we have to include all the security features that we have to include into a TCP/IP network. It didn't come secure in the first place. Here are all the protocols of the TCP/IP protocol suite. It's important to remember that each of these protocols runs on a different port. For example, FTP, the file transfer protocol, runs on port 21. Telnet runs on port 23. HTTP runs on port 80. SMTP, the simple mail transfer protocol, runs on port 25. The domain name system, DNS, runs on port 53. And each one of these uses a different port. And so you have to remember that when you're talking about all the different protocols of the TCP/IP protocol suite. IP addressing. IP version 4 addressing is the 4-byte 32-bit addresses that uniquely identify every device on the network. It is still the most common. The IP network address example here, 192 in this one, 192.168 is the network address, and the host address is 10.1. And notice it's not 10.1 or 168. It's the numbers are specified individually. The subnet mask is a network configuration parameter that defines the dividing line for a particular network. All hosts that share the same network address are part of the same subnet. IP version 6 addresses are 128 bits long, provide more unique device addresses, and are more secure because security is inherent in IP version 6. However, IP version 4, while many companies and organizations have moved to IP version 6, IP version 4 is still the most prevalent. Now, IP version 4, one problem with it, of course, we've already run out of IP version 4 addresses. So that's one issue. Because when you do the math, you've run out of so many devices, it's ridiculous. But using network address translation, a lot of organizations are able to create many, many more IP version 4 addresses because there are unique addresses within that organization that organization A would have one address, 10.10.10.2, that organization B would also have 10.10.10.2. So a network address translated address that's on the inside of a network is non-routable, non-reachable. You cannot key in that IP address and get a message to that device because you're sending it to the external IP address for that organization, and it's network address translated. There are many, many, many millions probably of 10.10.10.2s out there in the real world. Indeed, if you look at your wireless access point at home, and your IP address for your devices connect to it, you're going to see that they all have, the internal IP addresses that are common to network address translation, and somebody else's network would have the same IP address as well. Here again, the dynamic host configuration protocol, DHCP. It's used within a network to simplify the configuration of each user's computer. You get a request DHCP request to a router, and the reply comes back. It allows each computer to get its configuration information dynamically from the network instead of the network administrator providing the configuration to the computer. DHCP provides a computer with an IP version 4 address, subnet mask, and other essential communication information. The best example of this is that here on the Armstrong campus, every device has its own unique IP address. Now, In a very large organization, that's not usually possible. Um, but because we only have so many, maybe a couple thousand devices on this campus, um, we are able to do that. We're not hiding the addresses behind network address translation or using DHCP. We don't buy from our internet service provider a very large um, number of IP addresses. Each device here, so each drop, if you will, on the network has its own IP address. On the other hand, if you look at an internet service provider like Comcast, where they have a block of who knows how many millions of IP addresses they bought, every time that you connect to either a wireless access point or connect within especially within Comcast, that you're going to be delivered a different DHCP is going to deliver you a different IP address. And so when the session is done, that IP address is then released back to the internet service provider who can provide it to somebody else who wants to sign in. And the next time you're going to get a new IP address from DHCP. Some of the common ports again, I mentioned some of them before. Here you have 22 is secure shell. 110 is the post office protocol version 3, POP3. 139 is NetBIOS session service. 143 internet message access protocol IMAP, which allows us to uh, have our folder, or actually our email folders from one um, provider, email provider, and actually see it on two different devices. IMAP allows that. And then HTTP over secure sockets layer, HTTPS is 443. Uh, some more DNS, the domain name services 53. Um, FTP actually uses 20 for data and 21 for the control of it. FTPS, FTP over TLS, SSL uses 989 for the data and 990 for the control. And so that there you have those common protocols associated with different ports. NetBIOS uses those common ports, 137 the name service, 138 is the datagram service, and 139 is the session service. The secure copy part of SSH runs on port 22. SNMP, the Simple Network Management Protocol, for example, runs on 161. TFTP, the Trivial File Transfer Protocol, runs on 69. The Internet Control Message Protocol, ICMP, a management and control protocol for IP, delivers messages between hosts about the health of the network. ICMP tools, of course, ping sends a single packet to a target IP address, which is what we call an ICMP echo request, and traceroute uses ICMP echo request packets to identify the path that packets travel through a network. Now, one important point here, you don't want to allow external entities to ping your network. If they can identify which hosts, computers, servers, etc. are up and running and which are down. You only want ICMP and ping to be available internally for system and network administrators to be able to determine the health of the network that they administer. You never want in a firewall rule to allow external ICMP messages coming in from who knows where into your network. You need to block that protocol coming into your network and your firewall rules. So this is the end of part one. In part two, we'll discuss network security risks, tools, VPN technologies, and wireless concerns.